Hello everyone, welcome to Physics 205. So in this video, what I want to do is go over the solutions for the in-class practice problems on translational and rotational equilibrium. Okay, so in this first question, it says in the figure below, a girl is about to do a push-up. Her center of gravity lies directly above the point P on the floor, which is 0.9 meters from her feet. So basically it's saying like center of gravity is like right here, right, acting down. That's where her weight acts. This is the horizontal distance, 0.9 meters. And then it's 0.6 meters from her hands. And what we want to figure out is we want to figure out the force exerted by the floor on her hands, so up on her hands, and then by the floor on her feet. And we're going to assume like it's really two separate hands, but you can think of them as combined. We want the combine of the two forces acting on the hands. So you can think of it as like one force acting on the hands and one force acting on the feet. Okay, so to start, what I would do is let's draw this out just as like a stick figure to make it easier. So let's say here's the girl. Her weight is acting at the center of mass, right? So that's down. It's really a vector. And the force acting up, right, the floor on her hands, I'll call the FH for hands, acting on the hands. And then the force acting on her feet, I'll call F, say F, so force on feet, and that's really a vector. And we know this distance right here is 0.9 meters, and then this distance is 0.6 meters. What else do I know? Well, I know her mass too, right? Her mass is 54 kilograms. So if I want to calculate her weight, that's just mg. So that's going to be 54 times 9.8. So her weight is going to be 529.2 newtons. Okay, I want to calculate, let's find the force on her hands first. So to figure out this force, what I need to do is, first of all, I know that if she's just, let's say she hasn't started yet, right? She's just about to do a push-up. So she's definitely in rotational equilibrium, right? She's static. So that means the sum of the torques about any point that I choose as my axis of rotation has to sum to zero, right? The sum of the torques has to equal zero if you're in rotational equilibrium. So she's definitely in rotational equilibrium. She hasn't done a push-up yet. I can put the axis of rotation wherever I want, but because I have two unknowns, I don't know the force on her feet. I don't know the force on her hands. I want to eliminate one of those, and I can eliminate one of the torques by putting the axis of rotation at one of those points. If we're solving for the force on our hands first, I need that to remain in the equation. So what I'm going to do is I'm going to put the axis of rotation right here at her feet to start with. Okay, here I'll draw this again. So now I'm going to think of it like this. Here is the person. This is the axis of rotation, right? We have the force acting on her feet. We have her weight. And we have the force acting on her hands. Okay, I need to figure out the moment arms, right? Because ultimately, I want to sum the torques, and they have to give me zero, right? So I have a torque due to the force on her feet. I have a torque due to the weight, plus I have a torque due to the force on her hands, and that has to equal zero. And remember, torque is plus or minus the force times the moment arm. So I have to figure out all these moment arms. Well, remember the moment arm is defined to be the perpendicular distance from the line of action of the force. So if I start with the weight, right, this is the line of action of the force of the weight. So the perpendicular distance from that line of action of the force to the axis of rotation is just this distance right here, this horizontal distance. And we know that distance is 0.9 0.9 meters. So that's going to be the moment arm for her weight. And then the moment arm for her force on her hands. Well, again, this is the line of action of the force. So the moment arm is going to be the perpendicular distance, which is just this horizontal distance. And I can figure that out because I know if this is 0.9, this is 0.6. If I add them together, right, that's going to be the total distance here. So that's going to be the moment arm, which in this case is 1.5 meters. Okay, so now I can start working on these things. Torque due to the force on our feet. Well, in this case, since this line of action of the force on our feet goes right through the axis rotation, there's no moment arm. So this torque here, due to the force on the feet, is going to be 0, right? There's no moment arm. So that's just 0. What about the torque due to the weight? Well, the torque due to the weight is going to be the weight times the moment arm, which is 0.9. And if it were the only force acting, it would cause her body to rotate clockwise. So this torque is going to be negative. Remember, clockwise is negative and counterclockwise is positive. And then finally, the force on her hands. We don't know the force on her hands. That's what we're looking for, but we do know the moment arm. It's 1.5. And if that force were the only force acting, it would cause the body to rotate counterclockwise. So that torque is going to be positive. And that's got to equal 0. So I can solve this for FH now, right? If I bring the other term to the other side, I'm going to get 0.9 times W. And if I divide by 1.5, right, I have FH, force on the hands, is 0.9 times W, which we know, right? We already figured that out. It's 529.2 divided by 1.5. And that turns out to be 317.5 newtons. Okay, great. So we found the force on her hands. How do we find the force on her feet? One way of doing it, we could do this whole problem again, right? We could shift now the axis rotation to be at the hands, and then we could use the fact that the sum of torques has to be equal to 0, and we could solve for the force on her feet. That's one way of doing it, and that's fine. You could do it that way. Another way of doing this, since we know that she is not only in rotational equilibrium, she's also in translational equilibrium, right? She's static in the x and y directions. So we also know that the sum of the forces has to be 0 in the x direction and also in the y direction. It's really going to be the y direction that's important for this example, okay? And why is this true? Because she's in translational equilibrium. Right? Translational equilibrium. And then earlier we had the sum of the torques is 0 because she was in rotational equilibrium. Okay, so what I can do, let me use the sum of the forces in the y. So I want the y component of the force on the feet plus the y component of the weight plus the y component of the force on her hands. Well, the y component of the force on her feet, since all of that is acting in the positive y direction, right? We're assuming this is our coordinate system where y is pointing upward. So all of F, right, force on the feet is acting in a positive y direction. So this is just going to be plus FF. Do this in black again. All right, what about the weight? How much of the weight is acting in the y direction? All of it, but it's negative, right? So this is like minus W. And then the force on the hands, all of it is acting in the y direction. It's positive, so this is going to be FH equals 0. I can solve this for the force on the feet now. Right, so force on feet is simply going to equal, well, if I add W to both sides and then subtract FH, it'll be W minus FH. And if I plug in, remember her weight was 529.2. And then the force on her hands was 317.5. So then that's going to give me the force on her feet must be 211.7 newtons. Okay, so it's like you can think of it as, because it's static, her weight is being held up by the force on her feet and the force on her hands, right? And they're not the same. It's split differently only because her center of mass is not right in the center. If her center of mass was right in the center, then these would both be the same, right? They'd each be half of her weight. So it's like kind of distributed over her hands and over her feet. Okay, so those are our answers. All right, next question. The figure below shows a mobile consisting of 4 weights hanging on 3 rods of negligible mass. Okay, so when they say negligible mass, that means we don't have to think about this rod as having a weight. And then if it did, right, at the center of mass, the weight would be acting, which may not be at the axis of rotation. But we're assuming they're negligible, so we're going to not worry about those weights. We're only going to worry about these forces. Okay, find the value of each of the unknown weights if the mobile is to balance. So we're assuming this whole thing is in rotational equilibrium. So like each part is in rotational equilibrium. Okay, so what I'm gonna do is I'm gonna draw the bottom one first. We're gonna find W1 first. And then once we have that, we can figure out the tension in the string, right? Which will be pulling down here. We can keep working our way up once we have that. So I'm gonna draw that bottom part first. So it's like something like this. This is 2 newtons. This is some force upward. I don't know what that is. I'll call it F1. Really a vector. And then this is weight 1 acting down. And we want to figure out the magnitude of weight 1. And I know that this distance right here, this is 3 centimeters. And then this distance is 4 centimeters. By the way, if you convert that to meters, right, this will be 0.03 meters, and this will be 0.04 meters. Okay, because I don't know F1 and W1, I only want one of those unknowns to appear in my torque equation, right? We know that this is balanced right now, so we know that certainly that the sum of the torques must equal 0 about any point I choose as my axis of rotation. But I'm going to choose my axis of rotation to be right here to start, right at F1. Okay, because then only W1 will appear in my equation. I can solve for it. Okay, so in terms of moment arms, right, if these are the lines of action of the forces, then this is the moment arm for weight 1, which is just that 0.04 meters, right? That is the perpendicular distance. This is the moment arm for that 2 Newton weight, right? 0.03 meters. And in F1, since it goes right through the axis rotation, doesn't have a moment arm. Okay, so if I write this out, I have a torque due to the 2 Newton weight plus a torque due to weight 1 plus a torque due to F1. That's got to equal 0, right? Sum of the torques equals 0. So what's the torque due to the 2 Newton weight? Well, the force is the 2 newtons. The moment arm is 0.03. And since if that were the only force acting, it would cause us to rotate counterclockwise, this is going to be a positive torque. And then for the weight, I have W1, right? The magnitude of the weight. The moment arm is 0.04. And let's say, and it's also going, no, this case, if that were the only force acting, it rotate clockwise, right? So this is going to be negative. And then the torque due to F1, since it passes right through the axis rotation, it doesn't have a moment arm, that's just 0, right? So this is going to equal 0. So now if I solve this for W1, right, I'm basically going to get W1 times 0.04 is equal to 2 times 0.03. If I divide by 0.04, then W1 is going to end up being 1.5 newtons. Okay, so I have W1 now. All right, now that I have W1, I could find F1, right? If I use the fact that the sum of the forces in the y direction is equal to 0, then I have, I want the y components, right? In this case, they're all acting in the y direction. We can kind of just look at this. See how the F1 is positive? So I can have F1. The 2 newtons is negative, so -2, and then minus W1, right? That's also negative. That's got to equal 0. So if I bring those to the other side, F1 has to equal 2 plus W1. So it'll be 2 plus 1.5, which is what? 3.5, right? 3.5 newtons. Okay, why is that helpful? Because now if we go back to this picture, that means on the second rod here, this force pulling down must be the same as F1. And we know that now, right? We have that particular value. So that will allow us to find F2. If I isolate this as my system now, then I can figure out F2. And then once I have that, I can figure out this force, which I'm going to call F2. I can figure out weight 2 here. I can figure out this F2. And again, once I find that, that's going to be pulling down also F2. And then that will allow me to figure out W3. Okay, so we're doing like this in pieces. So this next piece, let me just do over here. I'm going to draw this as so this is W2. This is going to be my axis of rotation. This is F2. And then this is F1 acting down. And I know this distance is 2 centimeters, which is 0.02 meters. And this is 4 centimeters, which is 0.04 meters, right? And those, again, are the moment arms, because if I have my line of action, these are the perpendicular distances, right? From the line of action to the axis of rotation. So we haven't had to do any trig yet to figure out the moment arms, right? There's nice, easy horizontal distances. Later, in some of the later problems, we will have to do some trig to figure out the moment arms. Okay, so if I do sum of the torques is equal to 0. Well, I have a torque due to weight 2 plus a torque due to F1 plus a torque due to F2. That's going to equal 0. The torque due to weight 2 is going to be the weight times the moment arm. And since it would cause this thing to rotate counterclockwise, right, that'll be positive. Then the torque due to F1 is going to be F1, that magnitude, times the moment arm. And that would cause to rotate it clockwise, so that's going to be negative. And then the torque due to F2 is going to be 0, again, because the moment arm is 0, right? So that's equal to 0. So that means W2, if you solve for this, it's going to be F1 times 0.04 over 0.02. But we know F1 was 3.5, right? So 0.04 over 0.02. So I guess it's 2 times 3.5, which is 7. Right? This divided by this is just 2, right? So then it's going to be 7 newtons. Okay, so I have W2 is 7 newtons. And then to figure out F2, I can use this argument again, that the sum of the forces in the y must equal 0. So I have F2 acting up. The weight 2 is pulling down. F1 is pulling down. That's going to equal 0. So then F2 must equal the weight plus F1, right? I'm bringing those two terms to the other side. So then this is going to be, the weight 2 is 7, and F1 is 3.5, right? So 7 plus 3.5, which is 10.5 newtons. Okay, and then I can go, so now I have F2, right? I know this force pulling down. is 10.5. So now I can find F3 by looking at this as my system. So let me draw that last one out. And it's the same thing, right? Same thing we've been doing. So this is now F2 pulling down. This is the axis of rotation. Right here, we have another force, but we don't really care what this is. We could find it if we wanted to. Let's call F, and then W3. Ultimately, we only wanted to find the weights, right? And then this distance is 2 centimeters, so 0.02. And then this distance is, I think, 6 centimeters, so 0.06. I don't know why I just got this weird line in here, but I'm gonna erase it. I think my hand hits the screen sometimes and it gives me these stray marks. Okay, so 0.06 meters. All right. So again, the sum of the torques must equal 0. So I have a torque due to F2 plus a torque due to W3 plus a torque due to F. That's got to equal 0. And we know immediately that this one is 0, right? Because it has no moment arm. The line of action of F goes right through the axis of rotation. And then these moment arms for F2 and W3 are just going to be these horizontal distances, right? So the torque due to F2 will be F2 times the moment arm, 0.02, and it's positive torque, right? Because it would tend to rotate this thing counterclockwise, right? If I pull on this, it's counterclockwise. And then W3 is going to be W3 times the moment arm, and that one will be clockwise, which is negative, and that's going to equal 0. So in this case, we're solving for W3, right? It's going to be F2 times 0.02 divided by 0.06. And if you work this out, so this is 10.5 times 0.02 divided by 0.06. So it looks like that's gonna be like 1/3, right, of 10.5. So it turns out it's gonna be 3.5. So W3 is 3.5 newtons. Okay, and that's it. So we have all of our, we have W1 is 1.5, W2 we found over here somewhere. Here was W2 right here. It was 7. And then W3 was 3.5. So we found all the weights for that mobile. Okay, and that's what we're asked to find. Figure out all the weights. So we just had to do it by pieces, right? Assume each piece was in rotational equilibrium, solve for the weight, find the next piece, solve for the weight. But we had to use both the fact that it was in rotational equilibrium and translational equilibrium to figure out these forces in the tensions in the string here. Okay, and we could actually find this if we wanted to at the end, right? By using the sum of the forces in the y again. Now that we know F2 and we know W3, we could have found that as well. Okay, great. So not too bad, just took a little while to solve everything there. Next question. An individual wishes to measure the strength of their biceps by exerting a force on a strap connected to a force meter as shown in the picture. The strap is 28 centimeters from the elbow joint and the biceps muscle is attached at a point 5 centimeters from the elbow joint. If the force meter reads 18 newtons, what force is exerted by the biceps muscle? Okay, so here, I'm going to draw this out again using like a stick figure just because it's easier. So here is the forearm and hand. Here is the elbow joint. The biceps muscle, we're assuming is acting like just horizontally to the left here. So this is the muscle force. And then that strap, right, and that force transducer there, the force meter, is really exerting a force to the right of 18 newtons. Right? If you're pulling on it, remember, we're looking at the forces acting on the arm. So the force acting on the arm would be a force that this is pulling to the right on the arm of 18 newtons. Okay? And then what do we know? We know these distances, right? This from here to here is 5 centimeters, which is 0.05 meters. And then all the way down is going to be 0.28, I guess, right? So from here to here is 0.28 meters. Okay, they're definitely they're just holding it there, right? So it's an isometric contraction. So definitely it's in rotational equilibrium. So we know that the sum of the torques should equal 0. So I'm going to have a torque due to the muscle force plus a torque due to the 18 Newton force plus there's really a force here at the elbow joint. You can think of this as like a joint force. I'll call it like Fj. But so I have a torque due to Fj, but that torque is going to be 0, right? Because I'm assuming that the axis of rotation is right at the elbow. So there's no moment arm there. So this is basically going to be 0, right? There's no moment arm. And then the moment arms for these other forces, since this is exactly horizontal, it's just the perpendicular distance, which is at 0.05. And same thing for the 18th, so that's acting horizontal. This distance, 0.28, that's going to be the moment arm. That's the perpendicular distance. So the torque due to the muscle force is going to be the muscle force times the moment arm is 0.05. And if that were the only force acting, right, how would it rotate the arm about this elbow joint? It'd rotate it counterclockwise, so that's going to be positive. And then I have the 18 Newton force times its moment arm, which is 0.028. And that one, if it were the only force acting, it would rotate everything clockwise, right? So that's going to be negative. And that's got to equal 0. So we can solve this for FM, right? We wanted to find the muscle force. So if I solve this for FM, I'm going to add 18 and 0.28, 18 times 0.28 to both sides. So it just becomes positive right on the right-hand side. And then divide by 0.05. So now that muscle force is going to be like 100.8 newtons. Okay, so in order to perform the isometric contraction, the muscle force is like 100.8 newtons. And notice it's much larger, right, than this 18 Newton force that's resisting it. And the reason is you have a much smaller moment arm for the muscle force, right? The tendon attaches very close to the elbow joint. This force is acting really far away, a large moment arm. And it's the torque due to the muscle force has to equal the torque due to the 18 Newton force. Since the moment arm is larger for the 18 Newton force, then this force is going to have to be larger, right? It has a smaller moment arm, so that the product of the two, the force times the moment arm, which is the torque, those are going to balance out. So it makes sense. It's about 5 times as large, right? Almost 6 times, because this distance is like 6 times as large, so it's almost 6 times, the force is almost 6 times as large. All right, next question. So in this question, you're told one end of a uniform 100-kilogram beam, 10 meters long, is hinged at a vertical wall. It's held horizontally by a cable that connects to the beam 6 meters from the wall, as shown in the figure. And it's like, so it's 6 meters from the wall that it connects, and it's 8 meters up to the wall that it connects. And then a 400-kilogram weight is suspended from the end of the beam. Okay, so we have another force there due to that weight. So the question is, what is the tension in the cable? So this cable is going to be exerting a tension like this, right? We want to find the tension in that cable. And then also the vertical and horizontal forces acting at the hinge. There's going to be a joint force acting on the hinge here called Fj. And we want to find the components, right? We're assuming that X is to the right and Y is vertically upward. So we want to find fjx, fjy. So those three things we want to find. We want to find t, fjx, and fjy. Okay. The other thing we know is that this thing has a weight, right? So now this beam is not it's not massless anymore. It actually is a heavy beam. It's a 100-kilogram beam. Since it's uniformly dense, I can assume that the center of mass of that beam is right in the center. So like at 5 meters, and that's where the weight of the beam is going to act. Okay. So let me draw this out. Again, I'll draw a stick figure and then we'll calculate everything. Okay, so here is the wall. Here's the beam. So I'll just do this to signify a wall. It's not moving. This is the cable. Let me shorten this a little bit. So the center of mass of the beam is like right here. We know this distance is 5 meters, right? We know the total distance from here to here is 10 meters. And I know the beam attaches at 6, so this is 6 meters away. And I know this length here is 8 meters. What else do I know? I know at the axis of rotation, so we're going to consider this pin to be the axis of rotation. And ultimately, I'm going to find this is like the x component of that joint force, and then the y component. And I'm going to assume it's acting, I'm going to assume they're both positive. If I get negative, then I know that they're just going in opposite directions that I drew them in. Okay. And we know the weight, right? We know the weight that's hanging from the end here is 400. Wait, what was the weight here at the end? Oh, 400 kilograms is the mass. Okay. So we have a weight here equal to mg, where the m is 400 kilograms. And then we also have the weight acting here of the beam, which is the mass of the beam times g again. And the mass of the beam was what? I think it was 100, right? It is 100. Kilograms. Okay. So a couple of things I could do right off the bat. Let's just calculate those weights. So the weight of the beam is going to be the mass of the beam times g. So that'll be 100 times 9.8, which is equal to 980. And then the weight of, I'll call this the weight of the object, is the mass of the object times g. So this is going to be 400 times 9.8. So 4 times as large, right? 3920. Okay. I need to figure out all the moment arms now, right? Because ultimately I want to apply the fact that the sum of the torques has to equal 0. So these are easy. So the weights here, the perpendicular distance are going to be just these horizontal distances, right? So the moment arm for the weight of the beam, this one is going to be just this 5 meters. The moment arm for the weight of the object is going to be 10 meters. But for the cable, it's a little more complicated because now, so this is now the line of action, right, of the cable. So I need to figure out this distance, which is the perpendicular distance. That'll be like the L, the moment arm for the cable. Okay. So actually we can do that right now. Let me draw out the triangle here. We know the cable is attaching 6 meters away, right? And 8 meters up the wall. So something like this, where this is 6, this is 8. So I could figure out this angle here. We could just use trigonometry, right? We know that tan of theta is equal to opposite over adjacent. So that means theta is going to be inverse tan of that. And 8/6 is really the same as 4/3, right? So it's inverse tan of 4/3. And that turns out to be 53.1 degrees. And then ultimately, remember, I want the moment arm, I want this distance that's perpendicular, right? That's the L I want. So if I look at that new triangle, I have this. This is the right angle. So this is my right triangle now. I know this angle is 53.1 degrees. So if I'm looking for L, and I know that this is 6, this is now my hypotenuse, right? So what trig function relates, I guess this is opposite the angle, and this is the hypotenuse. That would be sine, right? So we know that sine of 53.1 degrees is equal to L over 6. So L is going to be 6 times the sine of 53.1 degrees. And that, draw that. Let me do this again. 53.1. That's going to equal 4.8 meters. Right, so that's the moment arm for the tension. Okay, so now that I have this, I can sum all my torques, right? So I'm going to sum all my torques, set them equal to 0. So I have a torque due to the tension. I have a torque due to the weight of the beam, plus a torque due to the weight of the object, plus a torque due to the joint force. That's going to equal 0. Now the torque due to the tension is going to be the tension times the moment arm, which we just found was L, right? I'll plug that in a second. And that one, if that were the only force acting, right, how would it rotate? So remember, the tension is pulling up like this. It would rotate this beam counterclockwise, right? So that's going to be positive. This is plus. Then torque due to the weight of the beam is going to be the weight of the beam times the moment arm, which is 5. And that torque, if it's the only force acting, it would be negative. And then the weight of the object is going to be the weight of the object times the moment arm, which is 10. That torque would also be negative. And then this torque is 0, right? Because the this would be like the joint force like this, right? That has those two, the X and Y components. It's passing right through the axis rotation. It's not contributing a torque. So this is going to equal 0. Okay, so I can solve this for the tension now. So tension, I'll bring these two terms the other side. Divided by L, right? So now if I plug in, this is what? The weight of the board was 980 times 5 plus the weight of the object was like huge, right? 3920 times 10, all divided by L, which we found L was 4.8. And if you work this out, it's going to be 9187.5 newtons. Okay, so that's the tension in that cable, right? That tension is 9187.5 newtons. Okay, now I want to find, so we found the first part. Now I want to find what is the X component of that joint force and the Y component of this joint force. Well, this whole beam is also in translational equilibrium, which means the sum of the forces must be zero, right? The sum of the forces in the x direction, sum of the forces in the y direction. Now, these are already going to be in the x and y directions directly. The weight is in the negative y direction. The object is negative y direction. What I do need to do is this tension here. All right, we just found this tension. So we calculated this tension. I need to find its components, right? It's going to have a component in the x direction, it'll be negative, and a component in the y direction. And then I can do some of the forces in the x, some of the forces in the y, and that will allow me to find the components of this joint force. Okay, so let's find the components of that tension first. Do I have more room here? Guess I can do it over here. So this tension, I'll draw it out again. It was acting in the second quadrant like this. Right, this is a tension. We knew this angle, right? We already found the angle is 53.1 degrees, this angle. That's kind of like our reference angle, 53.1 degrees. And I want to find the x component, so tx, and then the y component, because I'm going to need those when I do the sum of the forces in the x and y direction. So basically, if you extract the triangle that contains the reference angle, so this is 53.1 degrees. I know the tension, right? That magnitude was 9187.5. So that's hypotenuse is 9,187.5 newtons. And I want to find Tx, I want to find Ty. So since Tx is adjacent, it's going to involve cosine. But we have to be careful, it's negative, right? That component is negative, it's pointing to the left, so it's minus 9187.5 times cosine of 53.1 degrees. And that turns out to be 5516.4 newtons. And then the y component will be positive 9187.5 times sine of that angle. That turns out to be, so this one is negative, 7347.1. So 7,347.1 newtons. Okay. Now that I have that, now I can do my sum of the forces in the x is equal to 0, and then sum of the forces in y, right? Because now we're trying to figure out the components of that joint reaction force. And we know it's in translational equilibrium. So I want the x component of all my forces, right? I want the x component of the joint reaction force. I want the x component of the tension. I want the x component of what else? The weight of the beam, and the x component of the weight of the object. And that's going to equal 0. These are all x components. So fjx is just fjx, right? We're assuming it's going to the right, it's positive. If we get a negative answer, then we know it went to the left. The x component of t is going to be this minus 5516.4. The x component of the weight is 0, and the x component of the object, the weight of the object is also 0, right? They're both acting downward, not in the x direction, so equals 0. So this just tells us that the x component of the joint force is equal to 5,516.4 newtons. Which makes sense, right? It's basically opposing the negative x component of the tension, right? Because they have to be equal and opposite so that the whole thing is not accelerating in the x direction. And then we do the same thing for the y direction now. So I do sum of the forces in the y. So now I want the y component of the joint force plus the y component of the tension plus the y component of the weight of the beam. This is the y component plus the y component of the object. That's got to equal 0. So now fjy, well, the y component of the tension was positive 7347.1. The y component of the weight of the beam, that was negative, what was it? Negative 980. And then the y component of the weight of the object was negative 3920. Right, and that's got to equal 0. So then if I solve this for fjy, basically I'm bringing the two negative terms to the right-hand side to become positive, and then the 7,347.1 becomes negative. So this, if you work this out, is going to be negative 2, I think it's 447.1. Wait, let me double check this. So 980 plus 3920 minus 7347.1. Yeah, negative 2447.1 newtons. Okay, so what that means, because we assumed that the x component of the joint force was positive and the y component was positive, and we got a negative value for the y, it means that this actual joint force is acting in this direction. So we got positive for x, right? X, and we got negative for y. So it's acting like this in that direction. That would be the joint force. So really, I drew it. I just had to guess, right? And it's fine. We found out that actually it's going in this direction. That would be the joint force. Okay, a little bit of work, but again, all we did was we used the fact that it's in rotational equilibrium. So the sum of the torques has to be 0, and it's in translational equilibrium. So the sum of the forces in the x direction and y direction had to be 0. Okay, so we have all of our answers. We have the tension in the cable. We found that. We found the joint reaction force in the x direction and the joint reaction force in the y direction. Okay, next question. You're told a child of mass m is supported on a light plank. So we're assuming that the plank has no mass. That's what it means. Right, assume the plank is massless. Otherwise, we'd have to include another force here acting at the center of mass of the plank, acting down the weight of the plank. But we're going to assume there's no weight. By his parents who exert a force F1 and F2, as indicated in the figure, find the forces required to keep the plank in a static equilibrium. And then you're told that F1 and F2 should be written in terms of the child's mass. Okay, so we're not even given the child's mass. We'll just leave it all in terms of m. Okay, that's fine. All right, this is very similar to the first problem that we did, right? With the child doing the push-up, that girl doing the push-up. Very similar. So I'm going to draw this out. Here's the plank. Here is the mass of the child acting down, right? So this is gonna be the weight, which is the mass times g acting down. And then I'll call this F1 acting up here. And then F2 is on the guy's side right here. So that's F2. And we know that this distance is 3/4 L. Are we given that? Yeah, and then 1/4 L, right? So this is 3/4 of the total length of the plank, and this is 1/4 the total length of the plank. Okay, so let's see. Why don't we let's find F2 first, and we can do that by putting the axis of rotation right at F1, so F1 doesn't appear in the torque equation. So now if I do sum of the torques about that point equals 0, I have a torque due to F2 plus a torque due to the weight plus a torque due to F1, that's got to equal 0. And we already know the torque to F1 is going to be 0, right? There's no moment arm. These other moment arms are really easy again, because if this is the line of action, the perpendicular distance is just this horizontal distance, right? And then same thing for F2. It's going to be that distance. So the torque due to F2, will be the force F2 times the moment arm, which is basically L, right? It's the total length of that plank, whatever it is, L. And that one, let's see, it would tend to rotate it counterclockwise, so that's going to be positive, right? I'll just write a plus to remind you it's positive. Then the torque due to the weight will be the weight, which is mg, times the moment arm, which is 3/4 L. And that torque is negative, and that's got to equal 0. And then finally, if you solve this for F2, right, I'll bring the other term to the other side first. Then divide by L, right? Divide by L. And what's going to happen is that the L's will cancel here, and you're going to get 3/4 mg. So basically, remember, mg is the weight of the child. So basically 3/4 of the weight of the child, that has to be exerted by the person here. So the male person here pulling up. Because the child's sitting closer to him, it kind of makes sense. He's got to exert the larger force, and she can exert a smaller force here, right? And we found it's 3/4 of the child's weight has to be exerted at that point. Now let's find F1. Well, to do that, we could use torques again, but the easiest way to do this is just use the fact that we know it's in translational equilibrium now. So now I know that the sum of the forces in the y direction is equal to 0. Also in the x direction, but we have no forces acting in the x direction, so that doesn't matter. So sum of the forces in the y direction. So now I have the y component of F1 plus the y component of F2 plus the y component of the weight. That's got to equal 0. So the y component of F1 is this all of F1. The y component of F2 is all of F2. And then the y component of the weight is minus mg, right? And that's going to equal 0. So that means F1 is going to be mg minus F2. And we just found that F2 is 3/4 mg. Okay. Well, what's 1 mg minus 3/4 mg? That's just going to be 1/4 mg, right? Quick way of doing this is a factor on mg. So I have 1 minus 3/4. But remember, 1 minus 3/4, if I want to subtract fractions, I have to have the same denominator. So if I multiply this by 4 over 4, so I have the same denominator, this is like 4/4 minus 3/4, which is 1/4. So F1 is going to be just 1/4 of mg. Okay, so he has to exert the larger force here because the child is sitting much closer to him. He's exerting 3/4 the weight of the child, and she's exerting like 1/4 the weight of the child, and that will hold up the child, assuming that the weight of the board is negligible, right? If you had the weight of the board, you have to include that in too. Okay, so that wasn't too bad, right? That was similar to that first question that we did. And then the last question here, it says a student is holding an object in their hand and performing an isometric contraction. Okay, so we know it's in rotational equilibrium and translational equilibrium. The following values are given. The mass of the object is 5 kilograms. Okay, so we know the mass of the object, 5 kilograms, which, by the way, I can calculate the weight if I wanted to now, right? It's going to be m times g. So 5 times 9.8, which ends up being like 49 newtons. And the mass of the forearm and hand, so F and H, is 2.5 kilograms. So that means the weight of the forearm and hand, which is acting down here at the center, this is like the center of mass. This is the forearm and hand here. This is to be the center of mass of the forearm and hand. So that's where the weight acts. But I can compute the weight by taking the mass and multiplying it by g, right? It's mg. So this will be 2.5 times 9.8, which ends up being 24.5 newtons. Okay, so we know that the object is located 35 centimeters from the elbow joint. Okay, so we know this distance from here all the way to here is 35 centimeters, which I'll write in meters immediately. So it's 0.35 meters. And the center of mass of the forearm and hand is 20 centimeters from the elbow joint. So this distance here is going to be 0.20 meters. Okay, and the biceps muscle attaches at a distance 3 centimeters from the elbow joint. Okay, so then this little distance here is 0.03 meters. And what we want to do is we want to find the magnitude of that muscle force. So we want to find this M here. So we're calling the muscle force M, looking for that. And then we're also looking for the X and Y components of the joint reaction force. So again, we want FJX and FJY, where this is FJ right here, right? So we're assuming actually the X component is positive, the Y component is positive to start, and if we get negatives, then we know that this might be going a different way. Okay, so first thing we need to do, since they're performing an isometric contraction, right, we know that the sum of the torques must equal 0. But let me figure out what all these moment arms are. Okay, so I know if this is the line of action of the weight of the forearm and hand, then the perpendicular distance from the line of action of that force to the axial rotation, we're assuming the elbow joint is axial rotation, is going to be this distance right here. I'll do it in blue. Right, that distance. So this is going to be like, I'll call it L1. That's the moment arm for the weight of the forearm and hand. Then the weight of the object, this is the line of action. So the moment arm is going to be this distance from here over to here, right? I'll call that L2. That's the total distance across. And then the muscle force, this is the line of action of the muscle, right? So the moment arm is going to be this distance, the one that's perpendicular to it. Okay, so that's a little tricky to figure out, but we're gonna have to like draw these separately to figure all this out. Let me start with the weight of the forearm and hand first. Okay, so this is the elbow joint, right? This is the forearm. Let's say the weight of the forearm and hand is acting here. So I'm looking for that distance, right? And this is a right angle here, so this is like L1. And I know that, first of all, this is 30 degrees. And I know that this length right here is 0.2, right? It was 20 centimeters, so 0.2 meters. So how can I find L1? Well, L1 is adjacent to the angle, and I know the hypotenuse, right? This is my right triangle. So I can use cosine, right? Cosine of 30 is going to be adjacent L1 divided by the hypotenuse. So that means L1 is simply going to be 0.20 times cosine of 30. And that turns out to be 0.173 meters. Then I do the same thing for the weight of the object. So this is the weight of the object. This is the line of action. I'm looking for perpendicular distance, right, between the axial rotation and the line of action of the force. So that's my L2. I know that this again is 30 degrees. And I know the hypotenuse here is the full length of the forearm and hand, which is 0.35, right? So this is 0.35 meters. So that means L2 is going to be 0.35 times cosine of 30. And that turns out to be 0.303 meters. Okay, now I need to figure out the moment arm for the muscle. So in this case, I'm gonna have to draw this out because it's a little tricky here. All right, so for the muscle, again, this is 30 degrees, right? But then the muscle is pulling at an angle of 15 degrees from the vertical. So if I extend this up, the muscle is acting like this, right? This is 15 degrees. So we want to figure out if this is the line of action of the force. I want the perpendicular distance, which is going to be something like this. Right, wherever that is perpendicular. Okay, so let's see. I guess the way to figure this out is I know this angle right here is 60 degrees, right? Because if this is a right angle, then the angles of a triangle add up to 180, right? So I have 30 plus 90 plus 60, right? That's my right triangle right there. And then this angle right here is got to be the same as this. These are I think they're called vertical angles, right? So 15 degrees, this also has to be 15 degrees. So that means the total angle there, let me draw this again. This total angle must be 60 plus 15, right? Which is 75 degrees. Which means this angle now must be 15 degrees. Okay, so now that I know that that is 75, I know that the muscle attaches a distance of 0.03 meters away, right? So this length right here is 0.03 meters. And that's going to be the hypotenuse. And we're looking for the moment arm, which is this length right here, I'll call L3. So I guess I could use cosine again, right? If I use the 15 degrees. So L3 is going to be the hypotenuse times cosine of 15 degrees. And that is going to equal 0.029 meters. Okay, now that I have all these moment arms, I can do the sum of the torques now, right? So I'll do this on another page. Okay, so now I have sum of the torques is equal to 0. I have a torque due to the muscle force plus a torque due to the weight of the form and hand plus a torque due to the weight of the object plus a torque due to the joint force. That's got to equal 0. And again, because the joint force goes right through the elbow joint, there's no torque, right? There's no moment arm, so there's going to be no torque. Okay, torque due to the muscle force. Well, it's going to be the muscle force times that moment arm, which was L3. And that torque, if you look back at this picture here, it would tend to rotate. So if I pull up on M, it's going to tend to rotate this form and hand counterclockwise. So that's going to be positive. These other two torques, these are going to be negative, right? Because they are going to tend to rotate it clockwise. Okay, so that's positive. Then the torque due to the weight of the forearm and hand is going to be the weight of the forearm and hand times the moment arm, which we found was L1. and that's going to be negative, right? And then the weight of the object times L2, also going to be negative. That's going to equal 0. So if I solve this for the muscle force, M here, it's going to be the weight of the form in hand times L1 plus the weight of the object times L2, all divided by L3. Okay, and if we go back and plug in these values, the weight of the form in hand was 24.5. Let me just double check these. So the weight of the form in hand is right here, 24.5. Weight of the object was 49. And then I have all those moment arms, right? L1 was the moment arm for the weight of the form in hand, 0.173. The moment arm for the weight of the object was 0.303. And then the moment arm for the muscle was 0.029. Okay. So I'll plug this in. L1 is the weight, sorry, is the moment arm of the weight of the form in hand, which is 0.173. Then the weight of the object was 49. The moment arm for the object was 0.303. And divided by the moment arm of the muscle was 0.029. And if you work that out, you're going to get 658.1. So that is the muscle force. That's the force that the biceps would have to, assuming the biceps is the only muscle acting, right? That would be the force that the biceps exerts to keep the forearm and hand in that isometric contraction with that weight, holding that weight in your forearm and hand. Okay, what about the joint reaction force? How do we figure out the joint reaction forces now? Well, now we use the fact that the sum of the forces must equal 0, right? In the x direction and the y direction, because the forearm and hand is in rotational equilibrium. Now, the first thing we need to do, most of the forces are already in the x or y direction, but we have to resolve that muscle force. Here, I'll do that over here. So the muscle force, if I draw this out, we know the magnitude, right? We just found it, 658.1, but it was acting at an angle, so this is a muscle force, of 15 degrees, right, away from the vertical. Or if you want the reference angle here, you could do 90 minus 15, which is what, 75 degrees, right? So I want the x component, which is going to be negative mx here, and I want the y component of that muscle force. So if I use, let's just use the triangle that contains the reference angle. Again, it's just easier to always use a reference angle because then we know the x component will involve cosine and the y component will involve sine. And we know the magnitude of them, we just found it, was 658.1. So this hypotenuse is 658.1 newtons. So that means mx is going to be, first of all, it's negative. It'll be 658.1 times cosine of 75 degrees. And that turns out to be 170.3. So negative 170.3. And then my is positive 658.1 times sine is 75. By the way, you could also use, if you wanted to use this angle here, then the x component would involve sine of 15. But sine of 15 is the same as cosine of 75. And the y component would involve cosine of 15, which is the same as sine of 75. So it doesn't matter as long as you're consistent, as long as you know that those are really equivalent. If you work that out, it turns out it's 635.7 positive. Okay, so now that we have those muscle components, now we can actually sum all the forces. Right, so I'll do the x direction first. So I have sum of the forces in the x is equal to 0. So I have the joint force. I want the x component. I want the x component of the muscle force. I want the x component of the form and hand. And I want the x component of the object. That's going to equal 0. Well, we're assuming the joint force is positive, so that's just FJX. The muscle force in the X is negative, and it's going to be 170.3. And then these two are 0, right? There's no X component of the weight of the forearm and hand or the weight of the object. They're both acting straight down. So this just tells us that the X component of that elbow joint reaction force is equal to 170.3 newtons. Okay, so we have that. And then to find the Y component of the joint reaction force, I just have to do the same thing, but sum of the forces in the Y direction now. So now I have sum of the forces in the Y is equal to 0. So again, I'm assuming that the joint force is positive, so I'll just put a plus there. And if it's negative, it'll come out negative. Plus the Y component of the muscle force, plus the Y component of the weight of the forearm and hand, plus the Y component of the weight of the object. That's got to equal 0. So the Y component of the joint force is just FJY. The Y component of the muscle force is positive 635.7. The Y component of the weight of the forearm and hand is minus the weight of the forearm and hand, which is what, 24.5? Yeah. So minus 24.5. And then the weight of the object was 49 newtons, right? So, and it's negative, so it'd be negative 49, and that's going to equal 0. So then if I solve this for FJY, it'll be 24.5 plus 49, and then minus 635.7. I got to bring everything to the other side. I'm going to get FJY is equal to, actually it's going to be negative, I guess, negative 562.2. So negative 562.2 newtons. Great. So all this is telling us is that the X component was positive, right? So FJX is positive like this. And then FJY is negative. So the actual vector of that joint reaction force was actually like in the fourth quadrant. It's going down like this. It's going like that. That would be FJ, right? The vector, FJ. Okay. So if you go back to that picture here, I drew it as acting, right, where they're both components are positive, but really it's going in this direction, right? That joint force is really acting something like that. So really it'll be something like this. Because the X component is positive, but it turns out the Y component is negative, okay? But we didn't know that to begin with, so we assume a particular direction, and then when we did the calculations out, we got the correct components, whether they're positive or negative. All right, again, quite a bit to do there, but this, again, was nothing more ultimately than, because we're performing an isometric contraction, right? The forearm and hand is in rotational equilibrium, so the sum of the torques equals 0. And then, because it's also in static or translational equilibrium, that means the sum of the forces are also 0, right? Some of the forces in X are 0, some of the forces in Y are 0. And that's what we used to figure out the muscle force and then the joint force. We found the components. By the way, once we have the components, you could also find the actual joint force, the magnitude and direction, right? By using Pythagorean theorem and inverse tangent, but I didn't ask for that. But you could like convert it to polar form and find the magnitude of that joint force and the direction. Okay, so you could do that as well. The only thing that was trickier about this one is these moment arms were trickier, right? They weren't just nice, easy horizontal distances. We had to do a little bit of trig, especially with this muscle one. We had to figure out, it was acting at an angle of 15 degrees, and the arm itself was at 30 degrees. So we had to do a little bit of geometry here to figure out exactly what that moment arm was for the muscle force. So that was a little tricky. Okay, hopefully that was helpful. Thank you.